So this is the 6th section in the big integrations chapter, and we're adding another new tool to deal with awkward integrations, and this one is called integration by parts. And now I want to show you exactly where this comes from, and where we begin the process is actually not with integration at all, unsurprisingly, but we're going back to a tool for differentiating. And the tool for differentiating that we haven't really pulled apart yet is the product rule. So that is when, you remember, we have y equals some function of x, where my function of x can be written as the product of two different functions of x, some u of x multiplied by some v of x. And we had all sorts of examples of this. For example, we might have had x sine x, for example, really simple stuff. And in this case, u is x and v is sine x. And what we did was we devised a rule that said that dy by dx equaled u multiplied by dv by dx plus v multiplied by du by dx. So we had this product rule, which allowed us to separate up a function into two pieces, differentiate the two pieces, and recombine them to find the derivative. This is also quite commonly written as duv by dx equals u dv by dx plus v du by dx. This means just the derivative of uv is equal to this, and this just removes the y's and the x's entirely. If we're trying to differentiate a product uv, then we use the product rule. And what we can do is we can reverse engineer this to get a useful, convenient tool for doing some integration. Before I do that, I'm just going to reorganize this just slightly. So I actually want this in terms of u dv by dx as the subject of this, and therefore this equals the derivative of uv by dx minus v times du by dx. And at this point, I can just integrate all three terms. Right, we can integrate the three separate terms and it will stay equal. There's no issue with doing that. And what we end up with then is the integral of u dv by dx with respect to x is equal to, and something interesting happens to this one. This is the derivative of uv, and if I integrate a derivative, what I get back is just the original function, because integrating are inverses. So this just becomes uv minus the integral of v du by dx with respect to x. And this is the formula, right? This is the thing which we refer to as integration by parts. It doesn't feel on the surface very helpful. It looks a bit of a mess. It looks very complicated. But the basic principle here is that if I have a product of u and something that looks like a derivative we're familiar with, then I can rewrite that integral as a product of two things, and then the integral of v, which we had the derivative of before, and the derivative of u. Now, this can be incredibly useful because if the derivative of u is very simple, this integral here will be simpler than it was in the first place. Now, that will all unravel and become much more obvious when we begin looking at some examples of this. And before we do that, this is the textbook summary page. It just walks you through what I've just walked you through, basically. And what we're saying is we can use integration by parts if we're integrating something of this form, u dv by dx. And it's your decision what u is and what dv by dx is. And we'll talk about the logic behind that and what sensible choices are in the next couple of video clips.